A single galaxy, 16 million light-years long. Our entire Milky Way fits inside it 600 times over. We thought we understood how big the universe gets. We were wrong. Tonight, we travel from our own cosmic backyard out to the largest galaxy ever found through collisions. Black holes the size of solar systems, and structures so massive they challenge the laws of physics itself. We'll visit the beast that swallowed 1,000 galaxies, the jet of energy longer than most galaxy clusters, and the invisible wall that should be impossible to exist. If you enjoy the journey, like and subscribe, it keeps us going. Now, brace yourself. We begin. Step outside on a clear night, far from city lights, and look up. That pale smear stretching across the sky is our home, the Milky Way, and even from the outside looking in, it feels infinite. It spans roughly 100,000 light-years across. A light-year is the distance light travels in a full year, moving at about 600 million miles per hour. So 100,000 light-years means light, the fastest thing in the universe, would need 100,000 years just to cross our galaxy from one edge to the other. Stand at one end, shine a flashlight, and your great-great-great-grandchildren, multiplied across thousands of generations, would be long dead before that beam reached the other side. That number sits in your head for a moment, and it should feel big, because by everyday human standards, it is staggering. But here is the problem with human standards. They collapse completely the moment you start comparing galaxies to each other. The Milky Way has somewhere between 200 billion and 400 billion stars. Scientists are still refining that count, which is already telling. Our galaxy is so large that we cannot even agree on how many suns it holds. Its spiral arms twist outward from a dense central bar, curling through space in a shape that, seen from above, would look something like a cosmic hurricane, frozen in time. And still, when you stack the Milky Way against the largest galaxies we have found, it shrinks drastically. Imagine you built a scale model of our galaxy using a single grain of sand, one grain, sitting in the palm of your hand. Now, using that same scale, the largest galaxy we have ever discovered would be a boulder roughly the size of a large car. That grain of sand does not disappear inside the boulder, it vanishes. This is the kind of scale that breaks intuition completely. Most people learn in school that our galaxy is enormous, and they carry that idea through life. The Milky Way becomes a mental ceiling for cosmic size. Everything beyond it blurs into abstraction. But astronomers have spent decades discovering that the universe has no interest in human intuition. The cosmos builds things we were never designed to comprehend, and the largest galaxies are the clearest proof of that. They do not just challenge our sense of scale, they challenge our models of how galaxies form in the first place. Scientists built carefully tested equations to predict how big a galaxy should be able to grow. The largest ones we have found blow past those limits. And that is the part that keeps researchers up at night. Every time we find something bigger, something stranger, something that breaks the previous record, we are forced to ask a question that sounds almost philosophical. Did we misunderstand the universe? Or did the universe break its own rules? The answer matters. Because our entire framework for understanding how everything formed after the Big Bang depends on galaxy formation behaving in predictable ways. When galaxies grow beyond what the models allow, those cracks spread through the whole structure of cosmology. We are going to travel through all of it, starting from the familiar, then pushing outward, further and further, until the numbers stop meaning anything in the ordinary sense, and you are left sitting with the raw, unfiltered scale of what exists out there. But before we can understand the monsters, we need to understand how anyone figures out how big a galaxy actually is. And that process, it turns out, is far stranger and harder than most people imagine. Measuring a galaxy sounds straightforward. Look at it, find the edges, measure the distance between them. Done. Except galaxies do not have edges. That is the first problem, and it unravels everything. When you look at a galaxy in a photograph, you see a bright central region surrounded by a glow that fades outward. At some point, the glow becomes too faint to detect, and the image goes dark. That dark boundary looks like the galaxy's edge, but it is an illusion created by the limits of your camera, your telescope, your detector. Push those limits further, expose the image longer, build a more sensitive instrument, and the galaxy grows. More stars, more gas, more structure appears in what looked like empty space a moment ago. This is confirmed science, and it has reshaped our understanding of galaxy sizes dramatically over the past few decades. For most of the 20th century, astronomers measured galaxies by their visible light. They drew a circle around the bright stuff and called it done. Those measurements produced the numbers that ended up in textbooks, and those numbers were consistently too small. Then, instruments improved. Space telescopes launched above the atmosphere, which distorts and blocks certain wavelengths of light. Radio telescopes spread across continents, stitched together into arrays that could detect energy too faint and too long wavelength for optical cameras to catch. Infrared detectors revealed stars hidden behind clouds of dust, and suddenly galaxies started getting bigger, much bigger. The Milky Way itself went through this revision. For years, the standard estimate was around 100,000 light-years across. Then better measurements of stars in the outer disk pushed that to 160,000 light-years. Then discoveries of faint stellar streams, trails of stars pulled off smaller galaxies that our own consumed, extended the boundary further still. Some researchers now argue the Milky Way's full stellar halo, the diffuse cloud of old stars surrounding the main disk, stretches for several 100,000 light-years in every direction. So which number is correct? The honest answer is that it depends entirely on what you decide counts as part of the galaxy. Astronomers use several different definitions depending on what they are measuring. Some use the point where a galaxy's brightness drops to a certain threshold. Some trace the edge of the gas disk. Some follow the dark matter halo, the invisible mass that extends far beyond any visible stars. Each definition gives a different number, and all of them are scientifically valid for different purposes. This is not a flaw in the science. It is a reflection of reality. Galaxies are not solid objects with clean borders. They are systems, gradual, sprawling, blurry-edged systems embedded in a larger cosmic web. Here is why that matters for our story. When astronomers claim a galaxy is the largest ever found, that claim depends entirely on what measurement standard they used. And when a new record-breaking galaxy gets announced, the first thing other researchers do is challenge the method, the definition, the instrument sensitivity. Those debates are healthy. They are how science sharpens its picture of the universe. But they also mean that the title of largest galaxy ever found is not permanent. Every few years, with every new generation of telescope, something bigger turns up. Something that was sitting there all along, invisible to instruments that were not yet sensitive enough to see it. The current record holder was hiding in plain sight for decades. When it was finally measured properly, the number it produced stunned everyone who saw it. Most people carry the wrong number in their heads. Ask someone how wide the Milky Way is, and if they remember anything from school, they will say something like 100,000 light-years. That number is everywhere. Textbooks, documentaries, science websites. It has become the default. Scientists confirmed years ago that it is an undercount. The 100,000 light-year figure traces the visible disk of the galaxy, the flat, spinning plate of stars, gas, and dust that gives the Milky Way its spiral shape. That disk is real, it is measurable, and 100,000 light-years is a reasonable estimate of its diameter. The problem is that the disk is only one layer of the structure. Surrounding the disk is the stellar halo, a vast, roughly spherical region populated by old stars, globular clusters, and streams of stellar debris from smaller galaxies the Milky Way consumed long ago. The halo is diffuse. Its stars are spread thin. If you were floating inside it, you might see no nearby stars at all, just distant constellations indistinguishable from the view outside the galaxy entirely. But it is there, confirmed by observation, and it extends the true boundary of the Milky Way dramatically further than the disk alone. Measurements of distant stars and globular clusters push the stellar halo out to somewhere between 300,000 and 500,000 light-years from the galactic center. Some estimates go further. The uncertainty reflects the genuine difficulty of measuring objects that are both faint and spread across enormous volumes of sky. Then there is the dark matter halo. Dark matter is a confirmed component of the universe, detected through its gravitational effects on visible matter, even though it emits no light. Every large galaxy is surrounded by a halo of dark matter that extends far beyond its visible stars, and the Milky Way is no exception. Current models place our dark matter halo at somewhere around 1 million light-years across. Some models extend it to 2 million. At that scale, the Milky Way is not a flat disk at all. It is a roughly spherical system of unimaginable size, with its bright, familiar spiral buried at the center like the glowing yolk of an enormous invisible egg. And this version, the full Milky Way, including its dark matter halo, is one of the larger members of our local galactic neighborhood. The local group, the collection of galaxies gravitationally bound together around us and Andromeda, contains around 80 known members, and most of them are dwarf galaxies, tiny, faint systems with populations of stars that barely register compared to the Milky Way's hundreds of billions. We sit, in cosmic terms, near the top of a modest local hierarchy, but the word modest matters here, because outside our local group, the scale of galaxies begins to shift. Out there, in the wider universe, the Milky Way's full 1 to 2 million light-year extent stops being impressive. Out there are galaxies that make our dark matter halo look like a footnote. Understanding how enormous our own home actually is makes what comes next hit harder, because even with everything we just described, even with the invisible scaffolding and the ancient stellar halo and the billions of stars in the disk, the Milky Way is still only a medium-sized galaxy by cosmic standards. Somewhere out there, structures exist that dwarf it completely, and they formed through a process violent enough to reshape the physics of everything around them. For most of the 20th century, astronomers believed galaxies came in a predictable range of sizes. Small dwarf galaxies at the bottom, spirals like the Milky Way in the middle, and at the top, a class of large, roundish galaxies called ellipticals, which were understood to be bigger but still bounded by reasonable limits. Those limits turned out to be wrong, repeatedly, embarrassingly wrong. The reason the estimates kept falling short comes down to light. Astronomers measuring galaxy sizes in the early and middle parts of the 20th century were almost entirely dependent on optical telescopes, instruments that detect visible light the way human eyes do, just with far greater precision. And visible light, it turns out, captures only the brightest, densest parts of most galaxies. The faint outer regions, where star density drops and gas thins out, were simply invisible to those instruments. The technology produced a biased picture, one that showed only the core of the system and missed the sprawling, diffuse envelope surrounding it. Researchers knew their measurements were limited, but without better tools, they worked with what they had. When radio telescopes, infrared detectors, and eventually space-based observatories came online, the revisions began immediately. Galaxy after galaxy turned out to be larger than previously measured. The outer stellar populations, the extended gas disks, the diffuse halos, all of it appeared when the instruments gained the sensitivity to detect it. A typical large spiral galaxy, the kind that appears in textbooks as a representative example of galactic architecture, spans somewhere between 100,000 and 300,000 light-years across its visible disk. Its full system, including the dark matter halo, typically reaches 1 to 3 million light-years. These are enormous structures by any human-scaled measure, containing hundreds of billions to a few trillion stars. But here is what makes elliptical galaxies different. An elliptical does not have spiral arms. It does not have a flat disk. It is a three-dimensional, roughly egg-shaped or spherical blob of stars, with no clear internal structure beyond a gradual brightening toward the center. They are the product of collisions, the result of two or more spiral galaxies slamming into each other over billions of years until their structures blur together into something smoother and more massive. The largest ellipticals reach sizes that spiral galaxies simply cannot match, and the biggest of them all tend to sit at the centers of galaxy clusters, enormous gravitational hubs where hundreds or thousands of galaxies orbit a common center of mass. Over billions of years, those central giants pull in smaller galaxies, shredding them apart and absorbing their stars, growing larger with every meal. This process has a name in astronomy. It is called cannibalism, and the largest galaxies in the universe are the most successful cannibals in cosmic history. They grew by consuming their neighbors, slowly, relentlessly, over timescales that dwarf the current age of the universe, and some of them grew so large that our original models of galaxy formation had no framework to explain them. The ones that pushed furthest past those limits are a specific breed, and the most extreme example in the known universe involves something that shoots jets of energy into space longer than most galaxy clusters are wide. Andromeda is the galaxy we talk about when we want to explain what a collision looks like in slow motion. It sits roughly 2.5 million light-years away, close enough by cosmic standards to be visible to the naked eye on a clear night as a faint, smudged oval near the constellation with the same name. Most people who know about Andromeda know two things. It is our nearest large galactic neighbor, and it is heading toward us. The collision, they are told, is 4 to 5 billion years away. Plenty of time. Distant problem. But recent measurements changed the scale of that picture significantly. For most of the 20th century, Andromeda was measured the same way other galaxies were, by tracing its visible light. The disk of the galaxy, the bright central bulge and its surrounding spiral arms, spans roughly 220,000 light-years. A bit bigger than the Milky Way's visible disk, similar enough in structure and size to be considered our twin. Then, a team of researchers mapped Andromeda's full stellar halo, the extended cloud of old stars surrounding its main body, using a method that involved tracking individual bright stars at the galaxy's extreme outer edges. What they found forced a complete revision of the picture. Andromeda's halo extends for at least 2 million light-years in every direction from its center. Some regions of that halo show coherent streams of stars, structural features that stretch for hundreds of thousands of light-years, leftovers from smaller galaxies Andromeda, absorbed in the distant past. The halo is confirmed, observed, and enormous. Here is the implication that stops people cold. The Milky Way's own halo extends for roughly 1 to 2 million light-years. Andromeda's halo extends for at least 2 million light-years. The distance between the two galaxy centers is 2.5 million light-years. Do the math, and the conclusion arrives fast. The halos of the Milky Way and Andromeda already overlap. The two galaxies are already touching. The collision did not start 4 billion years from now. By some definitions, it started long ago, and we are already inside it. The stars themselves will not collide. Galaxies are mostly empty space, and when two spiral arms pass through each other, individual stars almost never make direct contact. But the gravitational disruption will be total. Orbits will be thrown into chaos. Stars will be flung out into intergalactic space. The spiral arms of both galaxies will be torn apart and stretched into long tidal streams before the two systems eventually merge into a single massive elliptical galaxy over the course of several billion years. Some astronomers call the future merged galaxy Milkomeda. Others use Milkdromeda. The name does not matter much. What matters is that the product of that merger will be a galaxy significantly larger and more massive than either of its parents individually. The Milky Way and Andromeda, combined, will become something closer to the class of large elliptical galaxy, still not in the extreme range, still smaller than the giants at cluster centers, but larger than what either one is today. That future merger is going to produce something impressive, and it still will not come close to matching the scale of what the universe's true giants have already achieved through millions of years of the same process, repeated on a far grander scale. The largest galaxies in the universe do not look dramatic at first glance. Point a telescope at one, and the image that comes back looks almost boring. A bright, featureless oval of light, brightest at the center, fading gradually toward the edges. No spiral arms, no dark dust lanes cutting dramatic lines through the disk, no star-forming regions glowing pink and blue with young, hot stars. Just a smooth, ancient, enormous blob of light. That understated appearance hides what these objects actually are. Giant elliptical galaxies are the graveyards of every galaxy that came too close. They form through mergers. When two spiral galaxies collide and combine, the result is an elliptical. When that elliptical sits at the center of a galaxy cluster, surrounded by hundreds of other galaxies all orbiting the same gravitational well, it begins a slow process of accumulation that can continue for billions of years. Smaller galaxies stray too close, get torn apart by tidal forces, and their stars get absorbed into the central mass. Medium-sized galaxies get consumed whole. Over time, the giant at the center grows. The stars inside a giant elliptical are overwhelmingly old, red and orange and dim, burning slowly on the last reserves of their fuel, having formed billions of years ago when gas was abundant and star formation was at its peak across the universe. The giant elliptical does not make many new stars anymore. It just accumulates more old ones. The largest confirmed giant ellipticals contain between 10 trillion and 100 trillion stars. The Milky Way holds somewhere between 200 billion and 400 billion. So, the most massive ellipticals contain something like 200 to 500 times as many stars as our entire galaxy, packed into a system that, at its widest measured extents, can span several million light-years. Their dark matter halos stretch even further. The boundary between a giant elliptical and the galaxy cluster it dominates becomes genuinely difficult to define at those scales. The galaxy and the cluster blur together, both embedded in the same enormous gravitational structure. One category within this class stands out even among the giants. Brightest cluster galaxies, the term astronomers use for the dominant galaxy sitting at a cluster's center, tend to be the most massive visible objects in the known universe. They are the endpoints of billions of years of cosmic cannibalism, and a few of them have grown so large that even the category of giant elliptical feels too small a label. These are the galaxies that first broke astronomers' models for how large a structure could reasonably grow. And the process that built them, the slow, grinding, gravitationally driven merger of galaxy after galaxy, leaves marks that are still readable billions of years after the collisions happened. Understanding what a merger actually does to a galaxy, to its stars and its structure and its physics, is essential before you can grasp why the true record holders are so extreme. Because a galaxy merger is one of the most violent events in the universe, even though it unfolds so slowly that any individual human lifetime would capture none of the motion at all. Two galaxies locked on a collision course sounds like the kind of event that ends everything. The reality is stranger, slower, and in some ways more terrifying than an explosion. Galaxy mergers do not happen quickly. The process takes hundreds of millions to several billion years from first approach to final combination. The two galaxies spend enormous amounts of time orbiting each other, passing through each other, swinging back around, and passing through again. Each pass distorts both galaxies, pulling stars and gas into long curved streams called tidal tails that can extend for hundreds of thousands of light years into the surrounding space. The two galaxies look, during this phase, like they are being pulled apart at the same time they are being pulled together. The stars themselves almost never collide. A galaxy is overwhelmingly empty space. If you shrank the Milky Way down so that our sun was the size of a grain of sand, the nearest other star would sit over 20 miles away. In a galaxy merger, two enormous collections of these widely spaced grains of sand pass through each other repeatedly. The grains do not hit, but their gravitational pulls on each other add up. Gas clouds, unlike stars, do collide. Gas can touch, compress, and slam into other gas. When two galaxies merge, their gas clouds crash together, and the compression triggers massive bursts of star formation. A galaxy that had been quietly aging suddenly blazes with the light of millions of newly born stars. These starburst events are among the brightest phases in any galaxy's life, and they burn hot and fast, exhausting enormous reserves of gas in a cosmically short period of time. Meanwhile, the supermassive black holes at the centers of both galaxies begin their own slow approach. These black holes, millions or billions of times the mass of our Sun, spiral toward each other as their host galaxies merge. Eventually, they too will combine, in a final merger that releases gravitational waves, ripples in the fabric of space itself, powerful enough to be detectable across billions of light years. By the time the merger finishes, the spiral structure of both galaxies is gone. The ordered, rotating disk, the spiral arms, the flat geometry, all of it has been scrambled by billions of years of gravitational disruption. What remains is an elliptical galaxy, stars moving on randomized orbits in every direction, orbiting a common center of mass that is now far more massive than either original galaxy was alone. Confirmed observations show that galaxies in the middle of major mergers display exactly these signatures: distorted shapes, long tidal tails, elevated star formation rates, and in some cases, two bright nuclei visible inside a single galaxy body, the two central black holes still separated but drawing closer. Every giant elliptical galaxy you see today carries the record of these past collisions inside its structure, and the largest ones carry the record of dozens of such events, stacked on top of each other over billions of years. There is one class of galaxy that took this process further than any other type of system known to science, and what it built in the process defies every expectation about what a galaxy is even capable of producing. In 2022, a team of astronomers working with data from a European radio telescope network published a finding that stopped the astronomy community mid-sentence. They had identified a radio galaxy with jets extending 16.3 million light-years from end to end. The galaxy itself sits around 3 billion light-years away from Earth. Its name, drawn from Greek mythology, is Alcyoneus, and its measured size is so far beyond any previous record that the researchers themselves went back and checked their calculations multiple times before going public. To understand why that number matters, you need a comparison that lands properly. The Milky Way spans about 100,000 light-years across its visible disk. Alcyoneus, measured from the tip of one jet to the tip of the other, is about 160 times that width. If you place the Milky Way inside Alcyoneus, you could fit the entire galaxy, including its disk, halo, and everything inside it, into the space of roughly 1% of the total structure. The previous record holder for largest radio galaxy had jets spanning about 6 million light-years. Alcyoneus beat that by more than 10 million light-years. A single discovery, a single measurement, expanded the known upper limit of galaxy size by a factor of nearly 3. The team confirmed the measurement using multiple independent methods. They used the LOFAR telescope network, a collection of radio antennas spread across Europe that can detect very low-frequency radio waves with extraordinary sensitivity. These low-frequency observations are essential for detecting old, faint radio emission, exactly the kind produced by the outer reaches of ancient jets that have been expanding for hundreds of millions or billions of years. The galaxy's visible body, the actual collection of stars at its center, is a giant elliptical with a mass roughly 240 times the mass of the Milky Way. Large, but within the known range of massive galaxies. The jets are the record breaker. They extend outward from the central black hole in nearly opposite directions, carrying plasma, magnetic fields, and energy at relativistic speeds across a distance that dwarfs almost everything else in the observable universe. The discovery forced an immediate revision of theoretical models for how large radio jets can grow. The previous understanding was that jets eventually slow down and spread out as they push against the surrounding intergalactic medium, the thin soup of gas that fills the space between galaxies. Alcyoneus reached a scale that suggested its jets were meeting far less resistance than expected, possibly because the region of space it inhabits is unusually empty, an underdense pocket in the cosmic web where jets can expand with almost nothing in their way. That explanation, still under investigation, opened a new question that researchers have not fully answered. If the right environment allows jets to grow this large, what is the actual upper limit? Is Alcyoneus the largest thing of its kind that the universe has produced, or is it simply the largest thing of its kind that we have found so far? The answer to that question depends entirely on understanding what radio jets actually are and how they grow to scales that seem physically impossible. The jets of Alcyoneus did not grow overnight. Scientists estimate they have been expanding for somewhere between several hundred million and a few billion years, pushed outward continuously by the energy output of the supermassive black hole at the galaxy's center. That black hole, confirmed to exist at the heart of the galaxy's elliptical body, is the engine. Everything else is the exhaust. When a supermassive black hole actively feeds, pulling in surrounding gas and dust, it does not consume everything. A fraction of the infalling material gets redirected. Magnetic fields near the black hole funnel some of the plasma into two opposing streams that shoot out perpendicular to the disk of infalling material. These streams travel outward at close to the speed of light in their innermost regions, carrying magnetic fields, high-energy particles, and enormous quantities of energy. In most radio galaxies, these jets eventually slow down, spread out, and dissipate as they push against the intergalactic medium. The intergalactic medium is thin, far thinner than the best vacuum achievable in a laboratory on Earth, but over millions of light years, even that thin resistance adds up. Most jets stall within a few 100,000 to a few million light years from their source. Alcyoneus stretched its jets 16 million light years. The gap between that and the previous record is the key clue to understanding why. Analysis of the region surrounding Alcyoneus suggests it sits in an unusually underdense environment. The cosmic web, the large-scale structure of filaments and voids that organizes matter across the universe, has regions where the intergalactic medium is significantly thinner than average. Alcyoneus appears to sit in or near one of these voids, a vast region of space where galaxy density and gas density are both lower than typical. Less resistance means jets travel further before losing coherence. The jets of Alcyoneus may have been expanding for longer and into emptier space than any other radio galaxy system currently known, which allowed them to reach a size that would be impossible in a denser environment. One additional factor researchers identified is the total mass of the galaxy's dark matter halo. Alcyoneus has a relatively low dark matter halo mass compared to other galaxies of similar stellar mass. This is unusual. Most massive galaxies sit in proportionally massive dark matter halos. A lower mass halo means the galaxy exerts less gravitational pull on the surrounding intergalactic medium, which may result in a slightly emptier immediate environment, further reducing jet resistance. The combination of an underdense cosmic environment and a lower than expected dark matter halo created conditions that allowed the jets to grow far beyond what models predicted for any known system. This is still an active area of research. Astronomers have not yet reached a consensus on the exact mechanism that made Alcyoneus this extreme. Some researchers suggest additional factors, including the age and continuous activity of the central black hole, played a significant role. A black hole that feeds steadily over a longer period produces jets that have more total energy invested in them, giving them more runway before they slow down. The jets of Alcyoneus are real, measured, and confirmed. What they are made of, and how they carry energy across 16 million light-years of space, is something the science makes very clear. And when you see what a radio jet actually is at the physical level, the scale becomes even more unsettling. A radio jet looks, on a telescope image, like a thin smear of light extending away from a galaxy's center. What it actually is involves physics extreme enough to redefine the word violent. When a supermassive black hole actively pulls in surrounding material, that material forms a disk before it falls inward, spinning faster and faster as it approaches the black hole's event horizon. The physics of that spinning disk, combined with the black hole's powerful magnetic field, produces a focused stream of plasma. This plasma is not ordinary hot gas. It is a mix of electrons and positrons, the antimatter counterpart to electrons, moving at speeds that approach the speed of light. The jet carries those particles outward, threaded through by magnetic field lines that keep the stream collimated, bundled tight, over distances that are genuinely hard to communicate. The energy inside a radio jet would vaporize anything in its path. A single large jet from an active galaxy carries more power than the combined output of trillions of stars. Some of the most powerful jets ever measured release energy, equivalent to billions of supernovae per year, sustained continuously for millions of years. Despite that energy, the jets are diffuse enough that they do not instantly destroy or even noticeably heat the sparse gas they travel through in the deep intergalactic medium. They push against it, compress it slightly at the jet's leading edge, and spread outward when they finally lose enough energy to dissipate. When the jet stops, the plasma it deposited spreads out into giant lobes of radio-emitting material, called radiolobes, that can be far wider than the jet itself. These radio lobes are what radio telescopes detect most easily. The electrons inside them spiral around magnetic field lines and emit radio waves as they do so. This process, called synchrotron radiation, can continue for hundreds of millions of years after the jet itself has gone quiet, which is why old, expanded lobes can be detected even from galaxies whose central black holes stopped feeding long ago. Alcyoneus is detectable because its lobes are still radiating. The LOFAR network picked up that faint radio glow at extremely low frequencies, traced the lobes outward from the galaxy's center, and measured the full extent of the structure. The 16 million light-year measurement includes both lobes and the span between them. A galaxy cluster, one of the largest gravitationally bound structures in the universe, typically spans somewhere between 10 and 30 million light-years. The jets of Alcyoneus span more than half the width of a large galaxy cluster. The structure these jets created rivals the scale of some of the largest structures that gravity alone can hold together. This raises a question that researchers have started taking seriously in recent years. If jets can grow this large, are they affecting the structure of the universe around them on scales larger than anyone previously considered? Are they heating, pushing, or reshaping intergalactic gas across regions wide enough to influence how galaxies form in neighboring parts of the cosmic web? The evidence for that kind of large-scale influence is still being gathered, but to understand what scale of structure the jets are operating inside, you need to understand the cosmic web itself, the vast, invisible architecture that organizes all matter in the universe. Pull back far enough, and the universe reveals a pattern. Galaxies do not scatter randomly through space. They cluster along thin filaments, enormous threads of gas and dark matter that stretch for hundreds of millions of light years. Where filaments intersect, galaxy clusters form, dense hubs packed with hundreds or thousands of galaxies bound together by gravity. Between the filaments lie vast empty regions called voids, stretches of space hundreds of millions of light years across that contain almost no galaxies at all. This structure, the filaments, the nodes, and the voids, is called the cosmic web. It is confirmed by observation, mapped across enormous volumes of the sky, and reproduced accurately by computer simulations of the universe's evolution, starting from the conditions just after the Big Bang. The cosmic web is the largest confirmed structure in the universe, and it is not a passive backdrop. It actively shapes which galaxies grow large and which remain small. Filaments carry gas. When a galaxy sits along a filament or near a cluster node, it has access to a continuous supply of gas flowing inward along the filament's length. That gas feeds star formation. It refuels the galaxy and keeps it growing. Galaxies that sit in filaments tend to grow larger and more active than isolated galaxies sitting in voids. Galaxy clusters form at the intersections of multiple filaments, and the gas flowing along all of those filaments drains toward the cluster center. Over billions of years, that drainage delivers enormous quantities of material to the galaxies sitting at the cluster's gravitational core. The dominant galaxy at the center, the brightest cluster galaxy, gets first access to all of it. This is one of the primary reasons that the largest galaxies in the universe tend to sit at cluster centers. The cosmic web funnels mass toward them like a vast system of rivers, all draining into the same lake. The filaments themselves are made partly of dark matter and partly of ordinary gas, primarily hydrogen. The dark matter provides the gravitational backbone, the invisible scaffold along which gas collects and flows. The gas, over billions of years, falls toward the densest parts of the filament, collects into clouds, and eventually feeds into galaxies. A filament can be several hundred million light-years long and a few million light-years wide. The gas inside it is so thin that it would qualify as an excellent vacuum by Earth standards. But distributed across such enormous volumes, the total mass it carries is staggering. Alcyoneus sits in an unusually underdense region, possibly near or within a void rather than a dense filament. That environmental factor contributes directly to its jet's extreme length. The largest galaxies at cluster centers, meanwhile, are products of the opposite environment. Maximally dense, maximally fed, surrounded by the gravitational convergence of multiple filaments over billions of years, those cluster center giants grew through a different mechanism than jet length. They grew through direct consumption, galaxy after galaxy absorbed over time, in a process that left them with star counts and physical sizes that no isolated galaxy can match. The most famous example of this kind of extreme cluster center growth is a galaxy that has been studied for decades and still manages to surprise researchers who look at it closely. Place a galaxy at the center of a massive cluster, and you have placed it at the bottom of the most extreme gravitational well in the known universe. Everything in the cluster is bound to the cluster's mass, which includes dark matter, hot gas, and all the member galaxies. The combined gravitational pull of all that mass creates a deep potential well, and the galaxy sitting at the very center of that well occupies the lowest point. Things fall toward it, slowly, relentlessly. Over billions of years, things fall toward it. This process is called dynamical friction, and it is one of the most important mechanisms in shaping the largest galaxies in the universe. When a smaller galaxy orbits inside a cluster, it creates a gravitational wake behind itself as it moves, a slight concentration of dark matter particles disturbed by its passage. That wake exerts a backward pull on the galaxy, robbing it of orbital energy over millions of years. The galaxy gradually spirals inward toward the cluster center. When it gets close enough, tidal forces from the dominant central galaxy begin stripping its outer stars. Eventually, the smaller galaxy is shredded and its stars are absorbed by the central giant. The central galaxy does not actively chase anything. It simply waits while physics delivers a continuous supply of material to its doorstep. Confirmed observations of brightest cluster galaxies show clear evidence of this process. Many of them show extended halos of diffuse stars around their main bodies, stretching for hundreds of thousands or even millions of light years, built entirely from stars stripped off smaller galaxies over billions of years. These halos glow faintly, far below the surface brightness detectable in older observations, but sensitive modern telescopes reveal them clearly. The hot gas inside a cluster also plays a role. Galaxy clusters are filled with plasma heated to tens of millions of degrees, so hot it glows in X-ray light. This intracluster medium, as it is called, loses energy over time through radiation and slowly sinks toward the cluster center. As it cools, It can condense and feed new star formation in the central galaxy or fuel the central black hole, which can then produce jets that reheat the gas and slow the cooling. This feedback loop, the cooling gas triggering the black hole which reheats the gas, is a confirmed process observed in many clusters, and it regulates the growth of the central galaxy. These clusters also merge with each other. When two galaxy clusters combine, their central galaxies eventually spiral together and merge as well. The product is a galaxy that inherited the accumulated history of both previous cluster centers, two giants becoming one. The mathematical models astronomers built to predict galaxy growth struggled to account for how efficiently these central galaxies accumulate mass over billions of years. Early simulations consistently underproduced the most massive galaxies observed. Researchers had to add more physics, more feedback mechanisms, more environmental factors, before the simulations could generate anything close to the scale of real cluster center giants. And even with all those additions, some of the most extreme examples still sit near or at the edge of what the models can produce. The galaxy that holds the record for size among visible stellar systems pushed those models harder than almost anything else researchers had found. Every large galaxy has one at its center. A supermassive black hole is not a detail. It is the engine around which the galaxy organizes itself, and its influence on the surrounding system is so profound that the black hole and the galaxy appear to grow together, each shaping the other across billions of years. The masses of these objects are difficult to hold in the mind. The black hole at the center of the Milky Way, called Sagittarius A star, has a mass about 4 million times greater than our Sunday. That sounds extreme. For a supermassive black hole, it is modest. The most massive black holes, confirmed by observation, carry masses of tens of billions of solar masses. Some candidates push toward 100 billion. The black hole at the center of a galaxy does two seemingly contradictory things over the course of a galaxy's life. It helps the galaxy grow, and it also limits that growth. When a black hole actively feeds, pulling in gas and dust from the surrounding region, it releases energy. The accretion process, the physics of materials spiraling inward before crossing the event horizon, is extraordinarily efficient at converting mass into energy. A small fraction of the infalling material escapes in the form of radiation, heat, and jets. This energy output can be enormous, sometimes outshining the entire galaxy's worth of stars combined. A galaxy in this active state is called a quasar or an active galactic nucleus, depending on how it is observed. That energy output does something critical. It heats the surrounding gas. Hot gas resists falling inward, so a black hole that feeds too aggressively heats the gas supply that was feeding it, cutting off its own fuel. This self-regulation mechanism is called feedback, and it is one of the primary reasons galaxies do not grow without limit. The largest galaxies in the universe, the ones at cluster centers, experience a specific version of this feedback. Their central black holes produce jets that push heat into the intracluster medium, preventing too much gas from cooling and collapsing into new stars. The jet feedback stabilizes the system, slowing the rate of star formation and keeping the galaxy from growing at its maximum possible rate. But the black hole also grows as the galaxy grows. More mass means a deeper gravitational well, which captures more gas, which feeds more growth, which deepens the well further. The black hole and the galaxy co-evolve over billions of years, their masses tracking each other in a ratio that holds surprisingly consistent across galaxies of wildly different sizes. This relationship, confirmed across hundreds of observed systems, suggests the two are not just coexisting, but actively regulating each other's growth. The most massive black holes in the universe sit inside the most massive galaxies. The galaxy that currently holds the record for largest visible extent has a central black hole measuring somewhere around 40 billion solar masses. For comparison, Sagittarius A star in the Milky Way is 4 million. The central black hole of this record-holding galaxy is 10,000 times more massive than our own. That galaxy is called IC 1101, and its scale challenges almost every instinct you have about how large a physical object can be. IC 1101 is the largest galaxy with a confirmed stellar extent in the known universe, and looking at it in a telescope image tells you almost nothing about what you are actually seeing. It appears as a soft, bright oval glowing against the darkness, centered in a cluster of fainter galaxies that surround it in every direction. The image looks like hundreds of other galaxy photographs. The scale is invisible unless you know the numbers. The galaxy sits about 1 billion light-years from Earth. It anchors the center of a massive galaxy cluster called Abell 2029, one of the largest gravitationally bound structures in its region of the universe. IC 1101 has been at that cluster's center for a very long time, long enough to have absorbed a staggering amount of surrounding material. The galaxy's confirmed stellar halo extends for roughly 6 million light-years. Some estimates, pushing to the outermost detectable edge of its diffuse starlight, reach higher. Its total mass, including its dark matter halo, is estimated at somewhere around 100 trillion solar masses. The Milky Way's total mass, including dark matter, sits around 1 to 2 trillion solar masses. IC 1101 outweighs our entire galaxy system by a factor of roughly 50 to 100. The number of stars inside it strains comparison. Where the Milky Way holds several hundred billion stars, IC 1101 contains somewhere in the range of 100 trillion. Line those stars up end to end at the average spacing of stars in our galaxy, and the chain would stretch far past the observable universe. How did it get this large? The answer is time and position. IC 1101 has occupied the center of a massive cluster for billions of years, possibly close to the age of the universe itself. In that time, it has absorbed galaxy after galaxy, each merger adding mass to the central system. The outer halo of diffuse stars surrounding its brighter central body is made almost entirely of stars stripped from those consumed galaxies, a graveyard of destroyed systems whose individual structures are long gone but whose stars still orbit the central mass. The galaxy also shows evidence of multiple past merger events preserved in its structure. The brightness profile of its stellar halo does not follow a single smooth curve. It shows subtle changes in slope at different radii, each one likely corresponding to a past merger event that added a new shell of stars at a particular distance from the center. This is a confirmed method of reading galactic history. Merger shells, as they are called, are a fossil record of a galaxy's violent past, visible if you measure the brightness profile carefully enough. The galaxy is currently quiet in terms of active star formation. Its gas has largely been consumed or expelled by past episodes of black hole activity. It sits, enormous and ancient, accumulating slowly from the remaining cluster environment, and yet, sitting inside it, you would never know the scale of what surrounded you. You would see stars, a sky full of stars. But the experience of living inside the largest known galaxy would be stranger than most people imagine. Imagine the Earth, unchanged, orbiting a sun exactly like ours. Same star, same distance, same temperature. But place that solar system deep inside IC 1101, somewhere in the outer halo region, about 2 million light-years from the galaxy's center. The first thing you would notice, looking up at the night sky, is that it looks emptier than ours. That sounds counterintuitive for the largest known galaxy. But the outer halo of IC 1101 is a region of diffuse stars spread across millions of light-years. The local stellar density, stars per cubic light-year, is actually lower than the stellar density in our neighborhood of the Milky Way. Stars in the halo are spread thin over an almost incomprehensible volume. The nearest star to our hypothetical sun might still be several light-years away, similar to our situation in the Milky Way. The sky would be dark most of the night. Familiar constellations would not exist. The stars around you would be old, cool, red, and orange, the long-lived survivors of an ancient star-forming era that ended billions of years ago. No blue giants blazing in the sky, no bright star-forming nebulae glowing nearby, just old light scattered across a quiet sky. But look toward the galaxy's center, roughly 2 million light-years away, and the view changes completely. The core of IC 1101, that dense, bright central bulge containing hundreds of billions of tightly packed old stars, would appear as an intensely bright band or glow stretching across a significant portion of the sky. Far brighter than the Milky Way looks from Earth, a concentrated river of ancient light, glowing steady and orange-white across the darkness. The surrounding cluster galaxies would also be visible to the naked eye. Hundreds of galaxies close enough and bright enough to appear as faint smears of light scattered across the sky. A gallery of entire galactic systems visible without a telescope. The night sky in IC 1101's cluster would be, in that sense, far richer with external galaxies than ours. But the emotional effect of looking outward from that position would be the most significant difference. From Earth, we look at the Milky Way and feel surrounded by something vast. From a position inside IC 1101's halo, you would look toward the center of your own galaxy and see something so enormous and so far away that the sense of scale would be almost impossible to process. The center of your galaxy is 2 million light-years away. Your galaxy is 6 million light-years wide. You are, in the outer halo, a small occupant of an almost unimaginably large system, sitting far from any dense neighborhood of stars, looking inward at a glow of ancient light that represents billions of years of cosmic accumulation, and that is the galaxy's visible extent. What surrounds IC 1101 beyond its stars is something that took astronomers a long time to recognize, because it cannot be seen in ordinary light at all. For a long time, astronomers drew galaxies where they could see them. The visible stellar disk, the spiral arms or elliptical body, defined the galaxy. Everything else, the surrounding space, was considered empty or, at most, sparsely populated with stray stars. Maps of galaxies showed clean, bounded shapes with a defined interior and an outside that simply was not part of the system. That picture was wrong, and dismantling it required building instruments sensitive enough to detect light far fainter than anything previous generations of telescopes could capture. The revision came in stages. First, spectroscopic measurements of gas at the edges of spiral galaxies showed something surprising. The gas was rotating too fast. According to simple gravitational physics, gas at the outer edge of a galaxy should orbit more slowly than gas closer to the center, the same way the outer planets in our solar system move more slowly around the sun than the inner ones. Instead, the rotation speed stayed roughly constant all the way to the outer edge of the visible disk and beyond. Something was providing extra gravitational pull, something invisible. That invisible mass became the dark matter halo, confirmed by decades of independent measurement techniques, including galaxy rotation curves, gravitational lensing, and large-scale structure surveys. The dark matter halo of a large spiral galaxy typically extends 10 to 30 times further than the visible stellar disk. A galaxy that appears 100,000 light-years across based on its stars may sit inside a dark matter halo 1 to 3 million light-years wide. For giant elliptical galaxies at cluster centers, the halos are even more extreme. IC 1101's dark matter halo stretches for tens of millions of light-years. At that scale, the halo overlaps with the halos of neighboring cluster galaxies, blending into the cluster's shared dark matter envelope. The boundary between the galaxy and the cluster effectively disappears. But dark matter was only part of the revision. The other part came from detecting extremely faint starlight at the outer edges of elliptical galaxies, light so dim that it sits 10,000 times below the brightness of the night sky as seen from Earth. Detecting it requires observing conditions so pristine that even scattered moonlight ruins the measurement. When astronomers achieved those conditions, using space-based observatories and specialized ground-based instruments, they found that the outer stellar halos of giant ellipticals extended far beyond what anyone had previously measured. Stars kept appearing at larger and larger radii. What had looked like a bounded system turned out to be surrounded by a diffuse glow of ancient stars stretching for distances comparable to or larger than the bright central body. This intracluster light, as it is called, is the collective glow of stars stripped from galaxies during cluster interactions and now orbiting freely inside the cluster without belonging to any specific galaxy. It is a bridge between the concept of a galaxy and the concept of a cluster, demonstrating that the two are connected by a continuum of matter rather than a clean boundary. The full extent of IC 1101, counting both its gravitational halo and its associated intracluster stellar component, makes it a system whose edges blur into the cluster itself. Measuring where this galaxy ends and where the cluster begins is a question the science has not fully resolved. And the reason that question is so hard to answer has everything to do with something that makes up most of the universe's mass, yet has never been directly observed. Remove dark matter from the universe, and every galaxy in existence falls apart. That statement is not dramatic license. It is the direct conclusion of decades of confirmed astrophysical observation. Dark matter provides the gravitational scaffolding that holds galaxies together, shapes their internal structure, and determines how large they can grow. Without it, the visible stars, gas, and dust would disperse into intergalactic space over time, because the gravity of ordinary matter alone is insufficient to keep them bound. Dark matter is confirmed to exist through multiple independent lines of evidence. Galaxy rotation curves show that stars at galactic edges orbit too fast for the visible mass to explain. Gravitational lensing, where the gravity of a massive object bends light passing near it, reveals mass concentrations far exceeding what visible matter accounts for. The large-scale structure of the universe, those filaments, nodes, and voids of the cosmic web, matches computer simulations only when dark matter is included. Remove it from the simulations, and the structure collapses into something that looks nothing like the observed universe. What dark matter is, at the particle level, remains unknown. It does not emit light, absorb light, or interact with ordinary matter except through gravity. It is genuinely invisible to every electromagnetic detector ever built. Its presence is known only through the gravitational effects it has on the things around it. This is confirmed scientific consensus. Every large galaxy sits inside a dark matter halo, a roughly spherical region of dark matter whose mass typically exceeds the visible stellar mass by a factor of 10 to 100. For the Milky Way, that halo extends to about 1 to 2 million light-years and contains a total mass roughly 10 times the mass of all the stars combined. For the largest galaxies in the universe, the dark matter halos are proportionally enormous. IC 1101's halo, estimated from gravitational measurements of the surrounding cluster, extends for tens of millions of light-years and contains mass equivalent to perhaps 100 trillion solar masses of dark matter, several times the mass of all its visible stars. The halo determines the galaxy's growth ceiling. A galaxy can only grow as large as its dark matter halo allows, because the halo's gravity is what captures infalling gas and holds it inside the system before it can form stars and build up the stellar mass. A larger halo captures more gas. A galaxy with an enormous dark matter halo, sitting at the center of a cluster whose shared dark matter envelope is even larger, has access to a mass reservoir that smaller, isolated galaxies cannot touch. This is why the largest visible galaxies tend to sit in the largest dark matter environments. The dark matter came first. It collapsed under gravity shortly after the Big Bang, forming the first structures in the universe. Ordinary matter fell into those dark matter concentrations afterward, collecting into gas clouds, triggering star formation, and eventually building the galaxies we observe today. The dark matter scaffolding dictates the architecture. Galaxies are, in a real sense, the visible decoration on an invisible skeleton. And that skeleton extends to scales far beyond any individual galaxy. The largest dark matter structures in the universe contain not just individual galaxies, or even clusters of galaxies, but collections of clusters spanning hundreds of millions of light years that no force in the known universe, not gravity, not jets, not anything we have identified, can hold together as a single bound system. Those structures have their own story, and they are stranger than anything we have covered so far. The biggest galaxies in the universe are also the most ancient. That connection is not coincidence. It is a direct consequence of how structure forms in a universe governed by gravity, dark matter, and time. The places that collected the most mass earliest became the seeds of the largest systems, and those systems have had the longest time to grow. In the first few 100 million years after the Big Bang, the universe was a nearly uniform sea of hydrogen and helium gas, threaded with tiny density fluctuations, regions where the matter was ever so slightly more concentrated than the average. Those overdense regions pulled in surrounding material through gravity. Dark matter clumped first, forming invisible halos. Ordinary matter fell into those halos next, producing the first stars and the first primitive galaxies. The regions with the highest initial density fluctuations grew fastest. They collapsed soonest, formed stars earliest, and attracted nearby galaxies soonest. By the time the universe was 1 billion years old, some of these regions had already produced massive galaxy clusters, dense hubs of star formation and galactic interaction. Observations confirm this. When astronomers point the most powerful space telescopes at the most distant regions of the sky, they see galaxies in the first billion years of the universe that are already surprisingly massive, already heavily built, already populated with old stars. This was a puzzle when those early observations first came in. The galaxies seen at extreme distances were more developed than the models of the time predicted they should be. The explanation involves the same process we have been following throughout this journey. The regions that became giant clusters were already accelerated relative to the average. They had more mass, more gravitational pull, more infalling material. From the very beginning, they ran ahead of the average pace of cosmic evolution, assembling mass faster than typical regions, forming stars earlier, exhausting their star-forming gas sooner. This is why the oldest, most massive galaxies in the universe stopped forming stars billions of years ago. They burned through their available gas supply early, in intense bursts of star formation, and then went quiet. The stars that formed in those early episodes are now ancient, red, and cool, having burned steadily for 10 or 12 billion years without replacement. A giant elliptical galaxy like IC 1101 is, in this sense, a museum of early cosmic history. Every star inside it formed in the ancient universe, most of them between 8 and 12 billion years ago. Looking at the galaxy is looking back at a period when the universe was far denser, far more active, far more violent than it is today. This early assembly of mass also means that the largest galaxies essentially ran out of growth fuel before the universe's star formation rate peaked. The universe as a whole formed the most stars per year at around 3 billion years after the Big Bang, but the giant cluster center galaxies had already passed their peak by then. Their black holes had heated their gas supply. Their star-forming material had been consumed. They grew afterward through mergers, absorbing other galaxies gravitationally rather than forming new stars from gas. Quiet accumulation rather than explosive formation. The universe's most extreme galaxies are, paradoxically, its most exhausted ones, ancient, enormous, and silent. And the reason for that silence opens a question about where all the gas went and why the universe's biggest galaxies essentially switched off their star-making machinery billions of years before smaller galaxies like the Milky Way did. Stars form from cold gas. That is the basic requirement. Gas needs to cool, compress, and collapse under its own gravity before nuclear fusion can ignite at the center of a new star. Any process that heats gas, disperses it, or removes it from a galaxy shuts down star formation. And the largest galaxies in the universe had multiple processes working against them simultaneously, each one feeding into the others in a cycle that eventually brought star formation to a halt. The first culprit is the central black hole. A supermassive black hole that feeds aggressively produces jets and radiation powerful enough to heat the surrounding gas and drive some of it out of the galaxy entirely in a massive wind. This process, called quasar-mode feedback, was far more common in the early universe when black holes were growing rapidly and feeding heavily. The energy released during those active phases was sufficient to expel significant fractions of a galaxy's gas reservoir, permanently removing the raw material needed for future star formation. The second process operates at the galaxy cluster scale. When gas falls into a massive galaxy cluster, it encounters the hot intracluster medium, the diffuse plasma filling the space between cluster galaxies, heated to tens of millions of degrees by the gravitational energy of the cluster's formation. As a galaxy moves through this hot environment, the surrounding pressure strips cold gas away from the galaxy's disk in a process called ram pressure stripping. The galaxy moves through the cluster, and its cold gas gets peeled backward, like water off a moving car in the rain, left behind in a trail that dissipates into the intracluster medium. The third process is strangulation. When a galaxy falls into a massive cluster, the cluster's gravity cuts off the galaxy's connection to the cosmic web filaments that were previously supplying it with fresh, cold gas. The galaxy's existing gas supply continues forming stars for a while, but with no new gas arriving to replace it, the star formation rate gradually declines and eventually ceases. All three processes operate more efficiently in the largest, most massive systems. The most massive black holes produce the most powerful feedback. The largest galaxy clusters have the hottest, densest intracluster medium, most effective at stripping and strangulating incoming galaxies. The cluster center giant experiences all of this simultaneously and from the inside, sitting in the most extreme gravitational environment in the universe. Scientists confirmed this pattern by comparing the star formation rates of galaxies across a range of masses and environments. Massive cluster center ellipticals show essentially zero ongoing star formation in the present universe. They are described as quenched, a term that captures the completeness of the shutdown. Smaller, isolated galaxies like the Milky Way are still forming stars. Our galaxy produces somewhere between 1 and 3 new stars per year on average, a modest rate sustained by the continued supply of gas from the surrounding environment. The Milky Way has not yet been quenched, but it will be, eventually, as we fall further into the gravitational influence of the local group and eventually merge with Andromeda. The environment around us will change. The resulting merger galaxy will exhaust its gas faster than either parent galaxy would have alone. A quenched galaxy does not die. Its existing stars keep burning, but it stops adding to itself. It becomes a record of its own past, carrying inside it the fossil history of every burst of star formation it ever experienced. Some galaxies have taken this concept to its logical extreme and become something so isolated and self-contained that astronomers gave them a name that captures exactly what they are. A fossil galaxy cluster sounds like a contradiction. A cluster, by definition, contains many galaxies. A fossil, in the astronomical sense, contains almost none. The term describes a specific end state. Imagine a galaxy cluster that formed very early in the universe's history, assembled its mass quickly, and then settled into a quiet environment where no new clusters or large galaxy groups fell into it for billions of years. With no fresh infalling galaxies to disturb its dynamics, the cluster's member galaxies slowly lost orbital energy through dynamical friction and spiraled inward toward the dominant central galaxy over billions of years. One by one, they were absorbed. The central giant grew. The cluster population shrank. Eventually, what remains is a vast X-ray glowing cloud of hot intracluster medium, the thermal signature of a once populated cluster, surrounding a single enormous galaxy that has absorbed nearly all of its former neighbors. The galaxy cluster is still technically there, defined by its dark matter halo and its hot gas. But the galaxies that once populated it are gone, merged into the central behemoth. This is the definition of a fossil cluster. Scientists confirm the classification by looking for a dominant central galaxy that is dramatically brighter than any other galaxy in the system, combined with extended X-ray emission from the hot intracluster gas that shows no recent major merger activity. The X-ray glow should be smooth and symmetric, the signature of an undisturbed system that has had billions of years to settle into equilibrium. Fossil clusters are relatively rare, partly because their formation requires a specific environment, an early forming cluster in a region of the cosmic web that happens to be isolated from further infall for a long time. Most clusters keep receiving new groups, and smaller clusters long into the universe's history, continuously repopulating their galaxy membership. The central galaxy of a fossil cluster is often among the most massive known examples of its kind. Billions of years of uninterrupted accumulation, without the gravitational disruption of new major mergers from outside, allows the central galaxy to absorb its cluster members steadily and grow to a size that clusters with more active merger histories do not always reach. These systems also provide astronomers with a clean laboratory for studying galaxy evolution, because the history of the central galaxy is less complicated than that of a cluster that has undergone multiple recent large-scale mergers. The fossil cluster's central galaxy has one dominant mechanism in its history: absorption of its own cluster members over a long, quiet period of time. The dark matter halo of a fossil cluster is enormous. The entire cluster's dark matter, originally spread across the halos of dozens of member galaxies, has largely been redistributed into a single smooth envelope centered on the dominant galaxy. The galaxy's effective dark matter mass is the cluster's dark matter mass, making it one of the most gravitationally dominant single systems in the universe. The universe contains both the most extreme individual giants, the largest galaxies by stellar extent, and the most extreme collective structures, the arrangements that contain those giants and millions of others bound together across scales that make even the largest galaxy look small. Understanding those larger structures requires stepping back far enough that individual galaxies disappear and only the architecture of the universe itself remains visible. At the scale of individual galaxies, gravity dominates absolutely. A galaxy is a gravitationally bound system. Its stars orbit a common center of mass, and will continue doing so for the remaining lifetime of the universe. Nothing short of another massive gravitational encounter will significantly alter that structure. Scale up to galaxy clusters and gravity still wins. A massive galaxy cluster, with its hundreds or thousands of member galaxies, its hot intracluster gas, and its enormous shared dark matter halo, is also a gravitationally bound system. Its members will not escape. Gravity holds them together on timescales comparable to the age of the universe. Scale up one more level to galaxy superclusters and gravity loses. A supercluster is a collection of galaxy clusters and galaxy groups that appear spatially associated, meaning they occupy the same general region of the universe. Laniakea, the supercluster that contains the Milky Way, spans about 500 million light-years and contains several hundred galaxy clusters, including the Virgo cluster, which is our nearest large cluster neighbor. By sheer volume, Laniakea is an enormous structure, but Laniakea is confirmed to be gravitationally unbound. Its member clusters are not orbiting each other, they are drifting apart under the expansion of the universe, accelerated by dark energy, the mysterious force driving the universe to expand at an accelerating rate. The clusters within Laniakea are moving toward their own local gravitational attractors rather than toward a common supercluster center. This distinction between bound and unbound structures is fundamental. A gravitationally bound structure will persist for trillions of years, its members staying together as the rest of the universe expands away. An unbound structure will dissolve over time, its member clusters dispersing into increasingly isolated islands as dark energy stretches the space between them. The largest gravitationally bound structures in the universe are massive galaxy clusters and a small number of systems, sometimes called great clusters or cluster complexes, that represent the upper end of what gravity can hold together against the expansion of space. Beyond that scale, structures exist, but they are temporary arrangements, coincidences of spatial proximity that dark energy will eventually erase. The question of what the largest possible gravitationally bound structure is has a specific answer tied to the physics of dark energy. Cosmologists calculate that structures larger than a certain mass threshold, roughly corresponding to the most massive galaxy clusters currently known, cannot remain bound against dark energy's influence on the timescales of the universe's future. Anything larger than that threshold is already dissolving, even if the dissolution takes billions of years. So the universe has a natural upper size limit for persistent structures. Everything above that limit is a temporary arrangement, a feature of the current epoch of cosmic history that will not survive into the far future. But within the current epoch, some of those temporary arrangements are staggering in scale. Mapping them required a revolution in observational astronomy, one that produced one of the most disorienting realizations in the history of science, that our own location in the universe is far stranger and more significant than we had assumed. In 2014, a team led by astronomer Brent Tully published a paper that redrew the map of our cosmic neighborhood in a way that surprised even professional astronomers. They were not just measuring positions of galaxies, they were measuring motions. The key insight was that if you map how galaxies are moving relative to the overall expansion of the universe, you can identify which galaxies are moving toward each other and which are moving apart. Galaxies flowing toward a common gravitational attractor belong to the same large-scale structure. Galaxies flowing away from each other belong to different structures. Using this velocity flow analysis, the team traced the boundaries of the supercluster containing the Milky Way. What they found was a structure spanning about 500 million light-years, containing roughly 100,000 large galaxies and an estimated mass of 100 million billion solar masses. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. The Milky Way sits near the outer edge of Laniakea. The flows of galaxies in our region of space show our cluster and its neighbors moving toward a region roughly in the direction of the constellation Centaurus, a gravitational attractor whose full nature is still being investigated. We are not at the center of our supercluster. We are in the outskirts, flowing toward a focal point we cannot fully see. That attractor, commonly called the Great Attractor, sits at the approximate center of Laniakea's velocity flows. Directly measuring it is difficult because it lies behind the Milky Way's own disk, in a region of sky obscured by the dust and gas of our galaxy. Astronomers have had to piece together its nature from observations at radio and X-ray wavelengths that penetrate the dust more effectively than visible light. The current understanding is that the Great Attractor corresponds to a massive concentration of galaxy clusters called the Norma Cluster Complex, combined with additional mass in the surrounding region, but researchers have found that Laniakea itself is flowing toward an even larger concentration further away, a structure called the Shapley supercluster, which is one of the most massive known concentrations of galaxies in the local universe. Our entire supercluster, all 500 million light-years of it, is drifting towards something larger. This chain of flows, pulling toward larger and larger concentrations, is a direct consequence of the cosmic web structure. Matter, concentrated in dense nodes, pulls on matter in surrounding filaments. Clusters pull on groups, superclusters pull on clusters. Everything flows toward the densest concentrations, on every scale, simultaneously. For humanity's sense of place in the universe, this is disorienting in a specific way. We grew up understanding Earth as orbiting the Sun as orbiting the Milky Way, the Milky Way as a member of the local group. Each step outward showed us to be smaller and less central than we thought. Laniakea adds another step. Our entire supercluster is a flowing, temporary structure that did not exist as a defined entity in our cosmological understanding before 2014. And even Laniakea pales against the largest named structures in the known universe. Structures so vast that their very existence forces a confrontation with the deepest assumptions of modern cosmology. For decades, astronomers noticed something strange in the motions of galaxies across a huge region of space. Galaxies were not moving purely with the expansion of the universe. Thousands of them, spread across hundreds of millions of light years in every direction, showed a systematic drift. They were all moving, on top of the universal expansion, toward a single point in the sky, a point sitting roughly in the direction of the southern constellation Centaurus. The scale of this peculiar motion was significant. Thousands of galaxies moving in coordinated deviation from what the expansion alone would predict. Something massive enough to gravitationally pull on systems spread across that enormous volume of space had to be sitting in that direction. Identifying it was the problem, because that direction happens to align almost exactly with the plane of the Milky Way's disk. When you look toward the Great Attractor, you are looking directly through our galaxy's densest regions, through enormous clouds of gas and dust that block visible light completely. Optical telescopes see almost nothing. The attractor hides behind our own home galaxy. Radio and X-ray observations cut through the obscuring material more effectively. Over decades of work, astronomers pieced together the picture behind the dust. What they found was a massive concentration of galaxy clusters, anchored most prominently by the Norma cluster and several surrounding structures, with a combined mass large enough to exert a measurable gravitational pull across hundreds of millions of light-years. The Great Attractor itself sits roughly 250 million light-years from Earth. The Milky Way, along with Laniakea and the Shapley supercluster region further away, are all drifting toward it at several hundred miles per second on top of the universal expansion. But here is the detail that expands the picture further. The Great Attractor is also falling. Astronomers confirmed that the mass concentration associated with the Great Attractor is itself moving toward an even larger structure, several hundred million light-years beyond it. The Shapley supercluster, one of the most massive concentrations of galaxy clusters known in the local universe. So the chain runs like this. Earth moves with the Milky Way. The Milky Way moves with the local group. The local group moves within Laniakea toward the Great Attractor, and the Great Attractor moves toward Shapley. Each system is a component of a larger gravitational flow, nested inside a hierarchy that keeps revealing another level when you step back far enough. At no point in this chain does humanity sit at a special location. We are participants in these flows, carried along by gravity on scales so vast that the motion takes hundreds of millions of years to cover any meaningful fraction of the distance. The Milky Way will never reach the Great Attractor. By the time any significant drift accumulates, dark energy will have expanded the universe enough to change the dynamics entirely. The Great Attractor is real, confirmed, and understood in its broad outlines. Its full mass and precise structure are still being refined as new surveys map the sky behind the galactic plane with improved instruments. And even this enormous gravitational hub, this mass concentration pulling millions of galaxies toward it across hundreds of millions of light-years, is a local phenomenon. The universe contains structures larger still, structures so large that their existence sits in direct tension with a foundational assumption of all of modern cosmology. The universe is expanding, and that expansion is accelerating. Dark energy, the force driving that acceleration, is confirmed by multiple independent observations. The apparent brightness of distant supernovae, the pattern of temperature fluctuations in the cosmic microwave background, and the large-scale distribution of galaxy clusters across the sky. It is the dominant component of the universe's energy budget, making up roughly 68% of the total energy content. Ordinary matter, including every star, planet, gas, cloud, and black hole in existence, accounts for only about 5%. Dark energy's effect on the future of galaxies is specific and irreversible. As the universe expands and the distance between galaxy clusters grows, the gravitational attraction between clusters weakens. At some point, clusters that are currently gravitationally bound to each other reach a separation where dark energy's repulsive effect outweighs their mutual gravitational attraction. At that point, they begin receding from each other permanently. This process is already underway for structures larger than the most massive galaxy clusters. Superclusters are dissolving. The member clusters within Laniakea are already drifting apart rather than orbiting each other. In the far future, billions of years from now, each galaxy cluster will become an isolated island, its member galaxies still bound to each other, but separated from all other clusters by an ever-growing and ultimately uncrossable void. Within those isolated clusters, the dominant central galaxy will continue accumulating mass for a while longer, absorbing whatever remaining cluster members still orbit close enough to spiral inward. The process slows as the supply of nearby galaxies diminishes. At some point, the cluster's population of infalling galaxies runs out. The central galaxy reaches something close to its final mass. For galaxies like IC1101, that final mass may not be dramatically larger than what it already is. The rate of galaxy infall into cluster centers has been declining as the universe ages and cluster populations thin out. The most intensive period of central galaxy growth, the era when mergers were frequent and the cosmic web was actively delivering mass at high rates, occurred billions of years ago. The universe's giant galaxies are, in all likelihood, past their peak growth phase. They will accumulate incrementally in the future, gaining mass in smaller steps as remaining cluster members slowly spiral inward. But the explosive growth of their youth, the intense merger and star formation episodes that built most of their mass, is over. What remains is a slow fade. Stars will age and die. The coolest, longest-lived stars, red dwarfs, will burn steadily for trillions of years, but the bright, hot stars that make galaxies visually dramatic are already gone from the oldest systems. The universe's most massive galaxies will grow dimmer over cosmic time, even as they grow marginally more massive. Eventually, over timescales far beyond the current age of the universe, even the longest-lived stars will exhaust their fuel. The galaxy will go dark, a vast collection of stellar remnants, white dwarfs, neutron stars, and black holes orbiting a central supermassive black hole in a universe too cold and too expanded for any new star formation to occur. Before that distant future, however, the universe still holds structures that challenge our understanding of physics at a far more immediate level. Structures so large that their existence forces a confrontation with what we thought was a settled question about the nature of the cosmos itself. In 2013, a team of astronomers mapping the distribution of gamma-ray bursts across the sky made a discovery they initially struggled to explain. Gamma-ray bursts are the most energetic explosions in the universe, visible across billions of light years, and because they occur randomly in galaxies throughout the cosmos, their distribution in the sky should reflect the underlying distribution of matter. They should be spread roughly evenly. Instead, the team found a concentration, an enormous clustering of gamma-ray bursts distributed across a region of the sky so large that, when converted to a physical scale at the estimated distance, the structure measured roughly 10 billion light-years across. For comparison, the observable universe spans about 93 billion light-years. This structure covered more than a tenth of the observable universe's diameter. The team named it the Hercules Corona Borealis Great Wall, after the constellations in the sky region where it appears. The estimated distance places it roughly 10 billion light-years away, meaning the light we detect from this region left when the universe was only a few billion years old. The structure existed in the early universe, when matter was still in the process of settling into the large-scale architecture we see today. The finding was immediately controversial, and remains so. Some researchers question whether the gamma-ray burst clustering truly reflects a single coherent physical structure, or whether it reflects statistical fluctuations and observational biases in the detection rate of gamma-ray bursts across that region of sky. The sample size of bursts detected in that zone, while significant, is not yet large enough for all astronomers to consider the structure definitively confirmed, but if it is real, and several independent follow-up analyses have found results consistent with its existence, it represents something that fundamentally breaks a core assumption of modern cosmology. That assumption has a specific name, and understanding why this structure violates it requires understanding what cosmologists mean when they describe the universe as smooth on large scales. Modern cosmology rests on a foundational assumption called the cosmological principle. The principle states that, on large enough scales, the universe looks the same in every direction and from every location. No special places, no special directions. Matter is distributed roughly uniformly. When you zoom out far enough, the filaments, voids, and galaxy clusters visible at smaller scales all average out into a smooth, homogeneous distribution at scales larger than a few 100 million light-years. This principle is confirmed observationally up to scales of roughly 1 to 2 billion light-years. On those scales, galaxy counts in different directions of the sky match each other within statistical expectations. The universe does look roughly uniform across those distances. The cosmological principle is also a necessary foundation for the mathematical equations of general relativity as applied to the universe as a whole. The standard cosmological model, called lambda cold dark matter, depends on the universe being homogeneous and isotropic at large scales. Remove that assumption, and the equations describing the universe's expansion, its age, its content, and its future need fundamental revision. A structure 10 billion light-years across violates the cosmological principle directly, a feature that large should be impossible under the standard model. The universe has simply not had enough time, given the speed of light and the age of the cosmos, to develop coherent structures of that scale through the gravitational processes we understand. Building a structure through gravity requires time and communication. Different parts of a structure need to have been gravitationally in contact with each other, meaning light and gravitational influence need to have had enough time to travel between them. At 10 billion light-years, the time required for the two ends of such a structure to have ever influenced each other exceeds the age of the universe. The two ends have never been in causal contact. If the Hercules Corona Borealis Great Wall is real and physically coherent, it formed through a mechanism outside our current understanding. Alternatively, it is evidence that the cosmological principle breaks down at scales larger than previously realized, which would require revising the equations that underpin our entire model of the universe. This is genuinely unsettling to cosmologists, not because the universe behaving unexpectedly is uncommon, but because the cosmological principle is load-bearing. It supports the architecture of the entire theoretical framework. If it fails at scales the observations suggest, the revisions required go deep into the mathematics of cosmology. The scientific community has not yet reached a consensus on the Great Wall's status. More data from large gamma-ray burst surveys and independent probes of the mass distribution in that region of the sky are needed. The debate is active, the stakes are high, and the outcome will matter regardless of which direction it goes. Either the structure is a statistical artifact and the cosmological principle survives intact, or it is real, and something fundamental about our model of the universe needs to change. Against this backdrop of structures that challenge our frameworks, the observable universe itself provides the final reference point, and placing everything we have discussed, from the Milky Way to Alcyonius to the Great Wall, inside that reference point produces a final perspective that is unlike anything else in science. The observable universe has a boundary. That boundary is set by the speed of light and the age of the universe. Light from any source further than a certain distance has not had enough time, in the roughly 13.8 billion years since the Big Bang, to reach us. We cannot see beyond that horizon. Objects exist beyond it, almost certainly, but their light is too young to have arrived. The observable universe spans about 93 billion light-years in diameter. That number is larger than you might expect from a 13.8 billion-year-old cosmos. But the universe has been expanding during the entire time light was traveling, stretching the distances between its origin point and us. The math of an expanding universe produces an observable radius of about 46 billion light-years in any direction. Inside that volume sits everything we can ever directly detect with any instrument, regardless of how powerful. Every galaxy, every cluster, every filament, every void, every cosmic structure we have ever measured or inferred or named exists within this sphere. Now place everything we have discussed inside it. The Milky Way, at 100,000 light-years across its visible disk, occupies a region so small relative to the observable universe that representing both on the same scale is essentially impossible. On a map where the observable universe is the size of Earth, the Milky Way would be smaller than a single bacterium. IC 1101, at 6 million light-years across its confirmed stellar extent, is 60 times wider than the Milky Way's disk. On that same map, it would be slightly larger than the bacterium, but still invisible to the naked eye. Alcyoneus, at 16 million light-years, from jet tip to jet tip, is the largest single galaxy structure confirmed in the known universe. On that map, it would be about the size of a red blood cell. The Laniakea supercluster, at 500 million light-years across, starts becoming visible. On the map, it would be roughly the size of a small ant. The Hercules Corona Borealis Great Wall, if confirmed at 10 billion light-years, would cover about 11% of the map's total diameter. It would be a continent, and the observable universe itself is the planet. Every galaxy, every cluster, every structure described in this entire journey sits somewhere inside that sphere, and beyond its edge, in directions we cannot see, the universe continues. Cosmological models suggest it extends far beyond what we can observe, possibly infinitely. The structures we have found, the record breakers, the cosmological principle challengers, may be representative of a universe that produces even more extreme examples in regions we will never be able to observe. This is not a comfortable thought for science to sit with. The observable universe is all we have access to. What lies beyond its horizon is, by definition, beyond any possible direct measurement. We can extrapolate from what we see and from our models, but we cannot confirm. What we can ask, based on everything we know from within the observable sphere, is whether a galaxy larger than Alcyoneus could exist anywhere inside it or beyond it, and what physical limits would determine the answer. Alcyoneus holds the current record, but science treats records as temporary. The question of whether anything larger could exist has a physical structure to it. There are things that promote extreme size, and there are things that limit it. The answer lies in how those two forces balance against each other across the range of environments the universe produces. Promoting extreme size in a radio galaxy requires three things working together: a supermassive black hole massive enough and active enough to sustain powerful jets over an extremely long period, an environment sparse enough that the jets meet minimal resistance as they expand, and enough time for the jets to propagate across the enormous distances involved. All three of these factors have upper limits. Black hole mass appears to have a practical ceiling in the range of tens to possibly 100 billion solar masses, set by the same feedback mechanisms that regulate galaxy growth. A black hole, feeding more aggressively than its environment can sustain, will blow away its own fuel supply, cutting off its growth. The most massive black holes known cluster near the upper end of this range. The environment has a lower limit on density as well. Even the deepest cosmic voids are not perfectly empty. Some gas, some dark matter, some residual intergalactic medium exists in every region of the observable universe. A jet expanding into an absolute vacuum would behave differently from one expanding into an extremely thin medium, but perfect vacuums do not exist on cosmological scales. Time is the most interesting constraint. Jets that have been active for longer have had more time to propagate further. The universe is 13.8 billion years old. A jet that has been running continuously since the early universe, supplied by a black hole that has fed steadily for 10 billion years, has had extraordinary time to build structure. Alcyoneus's jets may be among the older examples of radiojet systems currently known. The theoretical upper limit on jet length, given the most favorable possible combination of these factors, is a subject of active investigation. Some researchers have modeled scenarios where jets in the deepest possible cosmic voids, driven by the most massive possible black holes over the longest possible timescales, could reach lengths somewhat beyond what Alcyoneus has achieved. The margin above the current record is uncertain. There is also the observational limit to consider. Detecting an object the size of Alcyoneus requires an instrument sensitive enough to pick up extremely faint, low-frequency radio emission from old plasma lobes spread across millions of light-years. The LOFAR network achieved that sensitivity for the first time in the survey that found Alcyoneus. Prior to that survey, the galaxy was known, but its true extent was underestimated because previous instruments could not detect the outermost regions of its radio lobes. Surveys with even greater sensitivity are either planned or underway. As those surveys complete and cover more of the sky at lower frequencies, additional radio galaxies will be measured, and some of them may reveal extents comparable to or exceeding Alcyoneus. The current record may not survive the next generation of radio telescope surveys. Whether the next record breaker sits inside or outside the current range of expectations is not something science can answer with certainty today. What is certain is that the universe keeps producing surprises when our instruments improve. Every generation of telescope has found things the previous generation could not see, and every generation of findings has pushed our models to their limits and sometimes beyond them. In roughly 4 to 5 billion years, the sky above Earth will look nothing like it does tonight. Andromeda will dominate, already approaching at about 70 miles per second relative to the Milky Way. It will grow from a faint smudge in the constellation with its name to a vast, brilliant band of light stretching across the night sky. As the two galaxies draw closer and their gravitational interaction intensifies, both will begin to distort, their spiral arms pulling into long tidal streams, their shapes losing the clean structure they have today. The actual passage through each other will take hundreds of millions of years, during which the gravitational disruption triggers a massive burst of star formation as gas clouds throughout both galaxies collide and compress. The sky, for any surviving observer, will blaze with the light of millions of newly born stars, hot blue giants scattered across a sky, dominated by the chaotic merged structure of two galaxies in collision. The two systems will pass through each other, swing apart slightly, then fall back together over another few 100 million years. After 1 to 2 billion years of this dance, the two galaxies will fully combine into a single merged system. Astronomers call the expected result Milkomeda, or sometimes Milkdromeda. By most predictions, the merger product will be a large elliptical galaxy, its spiral structure erased by the gravitational disruption of the collision, its stars moving on randomized orbits around the merged central mass. The Sun will almost certainly survive this event. Individual stars, including our own, are vanishingly unlikely to collide during a galaxy merger. The Sun may be flung to a new orbit, perhaps far from the merged galaxy's center, but the change in stellar behavior will be gradual. Earth's orbit around the Sun is expected to remain stable throughout the merger process. The merger will also bring the two central supermassive black holes into eventual collision. Sagittarius A star, the Milky Way's 4 million solar mass black hole, and Andromeda's central black hole, estimated at roughly 50 to 100 million solar masses, will spiral toward each other over billions of years and eventually merge. The merger will release gravitational waves detectable in principle, across enormous distances. The resulting black hole will carry the combined mass of both progenitors. Milky Way will be a large elliptical galaxy. Its star count will exceed 1 trillion. Its dark matter halo will span several million light-years. By the standards of the Milky Way today, it will be enormous. By the standards of IC 1101, it will still be modest. By the standards of the structures we have explored furthest in this journey, it will be completely unremarkable. The largest galaxies in the universe grew through this same merger process, repeated dozens of times, sustained by cosmic-scale gravitational environments and billions of additional years of accumulation. What we will become in 4 billion years is a version of what those galaxies were at an early stage of their own history. And yet even the largest of them, Alcyoneus and IC 1101 and the others, carry a form of impermanence. Not because they will disappear quickly, but because every observation we make of them comes filtered through something that changes what we are actually seeing, the irreducible delay of light across cosmic distances. Every observation in astronomy is a time machine, and it only goes in one direction. When you look at a galaxy 1 billion light-years away, the light reaching your telescope left that galaxy 1 billion years ago. The photons you are detecting were emitted when the universe was nearly 1 billion years younger than it is today. You are seeing that galaxy as it was at that moment in its past, not as it exists now. This is a confirmed, unavoidable consequence of the finite speed of light. Light travels at about 600 million miles per hour in a vacuum, which is extraordinarily fast by any human standard, but laughably slow when measured against cosmological distances. At those distances, travel time becomes meaningful in a way that fundamentally changes what observation means. The Andromeda Galaxy, our nearest large neighbor, sits 2.5 million light-years away. The image we see tonight shows Andromeda as it was 2.5 million years ago. The hominid ancestors of modern humans were just emerging in Africa when that light left Andromeda. Whatever is happening in Andromeda right now, we will not find out for another 2.5 million years. Alcyoneus sits roughly 3 billion light-years away. When the light that reveals its 16 million light-year jet extent left that galaxy, Earth did not yet exist. Our solar system formed about 4.5 billion years ago. Alcyoneus, as we observe it, predates our planet. IC 1101 sits about 1 billion light-years away. Its light left when Earth's multicellular life was only beginning to develop in shallow seas. The galaxy we describe as the largest known by stellar extent is a picture from 1 billion years in the past. This has a direct practical consequence for the question of what is currently the largest galaxy in the universe. We do not know. We cannot know. We can only know what galaxies looked like at the time their light departed for us. And for different galaxies, that departure time differs enormously. We are comparing snapshots from different epochs and treating them as a simultaneous picture because no alternative exists. The universe as it currently exists, the real-time state of every galaxy and structure at this actual moment, is permanently inaccessible to us. The Milky Way is the only galaxy we observe in anything close to real time, and even within it, stars at the far edge of the disk are seen as they were 100,000 years ago. This is a genuine limitation, not just a technical one. It is woven into the physics of how information travels through space. The universe has a speed limit, and that speed limit means that astronomy is always, inevitably, history. What this implies for our census of cosmic giants is specific. The largest structures we have found might not be the largest structures that exist right now in the observable volume. They are the largest structures we can detect given the particular combination of distances, travel times, and instrument sensitivities that define our current observational reach. And what exists in the regions of the observable universe we have not yet surveyed thoroughly, at the sensitivities required to detect the most diffuse and extended structures, remains genuinely unknown. The universe's inventory of its most extreme objects is still being taken. The largest structures we have found were found because our instruments finally became sensitive enough to see them. Alcyoneus was known before 2022. It was classified as a radio galaxy. Its extent was estimated from earlier surveys. Those estimates were significantly too small because previous instruments could not detect the faint, low-frequency emission from the outermost regions of its plasma lobes. When LOFAR surveyed it with greater sensitivity at lower frequencies, the true extent revealed itself. This pattern repeats throughout the history of observational astronomy. Objects are detected, measured, and placed into categories. Then better instruments look again, and the measurements change, sometimes dramatically. The Milky Way grew substantially when better techniques measured its outer stellar populations. Andromeda's halo tripled in estimated size when faint stellar streams were mapped properly. Individual galaxy clusters revealed extended gas halos when X-ray observatories revealed emission too faint for earlier instruments. Every generation of telescope improvement has found structures that the previous generation could not fully detect. The logical implication is that the current generation of instruments is itself producing an incomplete picture. Structures exist within the observable universe that our current best instruments would either misclassify or miss entirely if those structures are faint enough, large enough, or at the wrong wavelength range for existing surveys. Radio telescope networks like LOFAR and its successor projects are already extending sensitivity to lower frequencies and greater angular scales. Next-generation surveys planned for the coming decades will map the low-frequency radio sky with far greater depth than any previous instrument. Optical and near-infrared surveys are using increasingly sophisticated methods to detect intracluster light and diffuse stellar halos around the most massive galaxies. X-ray observatories are probing intracluster gas to greater distances and fainter surface brightnesses than before. Each of these improvements will produce discoveries. Some of those discoveries will be record breakers. A radio galaxy with jets longer than Alcyoneus almost certainly exists within the observable volume. A galaxy cluster with an even more massive central galaxy than IC1101 may already be catalogued, but not yet fully characterized. Beyond the observable horizon, the question becomes philosophical in a specific sense. Cosmological models predict that the universe extends far beyond what we can see, possibly infinitely. If it extends infinitely, then every possible configuration of matter that physics allows exists somewhere, including structures far larger than anything in our observable patch. The physics does set limits. The jet length limit imposed by black hole mass, jet lifespan, and intergalactic medium density means that radio jets cannot grow without bound. The stellar extent of a galaxy is limited by the size of its dark matter halo and the available mass in its environment. These physical limits apply uniformly across the universe, not just in our observable region, but within those physical limits, there is room for structures somewhat larger than what we have found. And given the improbability-defying scale of what we have found already, the prospect of something even more extreme sitting beyond the next improvement in instrumental sensitivity carries real scientific weight. The universe has surprised us every time we looked harder. There is no particular reason to expect that to stop now. Every time a new record-breaking structure is confirmed, two things happen simultaneously in the astronomy community. First, there is a burst of excitement at the discovery itself. Second, there is a quieter, more intense conversation among theorists about whether the standard model can accommodate it. The standard cosmological model, lambda cold dark matter, has been extraordinarily successful. It correctly predicts the large-scale distribution of galaxies across the sky, the temperature fluctuations in the cosmic microwave background, the age and expansion history of the universe, and the relative abundances of light elements formed in the first few minutes after the Big Bang. No competing model matches its predictive power across that range of observations. But extreme scale structures stress it in specific ways. The most massive galaxy clusters sit at the edge of what the standard model predicts should exist in a universe of this age. Finding a cluster significantly more massive than the model's statistical expectations would require either revising the model's parameters or introducing new physics. So far, the most extreme known clusters fall within the model's predicted range, though barely. Galaxies like Alcyoneus, with jet extents far beyond previous records, are not directly predicted by cosmological models, but are more a challenge for galaxy formation models specifically. The conditions that produce jets of that length, the underdense environment, the sustained black hole activity, the particular dark matter halo properties, need to be reconciled with models of how radio jets interact with their environments. Those models are being revised in response. The Hercules Corona Borealis Great Wall presents the most fundamental challenge. If confirmed at its estimated scale, it directly violates the cosmological principle, the foundational assumption on which the standard model's equations are built. This would require not a revision of parameters, but a restructuring of the theoretical framework itself. The stakes of that confirmation, or disconfirmation, are as high as anything in observational cosmology today. There is a productive tension in this situation. Models that are never challenged never improve. The history of cosmology is a history of observations that did not quite fit, forcing model revisions, those revisions producing new predictions, those predictions tested by new observations. The standard model itself emerged from earlier frameworks that failed to account for what observers found. The extreme structures we have been exploring, the giant ellipticals, the record radio galaxies, the enormous cosmic web features, are doing exactly what good observations should do. They are testing the model at its limits, revealing where it needs refinement, and pointing toward the physics that any improved model will need to incorporate. Some of that physics is already being explored. Modified theories of dark matter, revised models of dark energy, extensions of general relativity at cosmological scales, all of these are active research programs, driven partly by the need to explain observations that strain the standard model. The universe is not broken, our picture of it is incomplete, and the largest structures in it are the most powerful tools we have for figuring out in what specific ways that picture needs to be extended. Step back one final time and hold the full picture. You are standing on a rocky planet roughly 8,000 miles wide, orbiting a star approximately 860,000 miles across, located about 26,000 light-years from the center of a galaxy 100,000 light-years in diameter. That galaxy contains somewhere between 200 and 400 billion stars and sits inside a dark matter halo roughly 1 to 2 million light-years wide. Your galaxy is one of approximately 80 members of the local group, a gravitationally bound association of galaxies spanning about 10 million light-years. The local group, in turn, is one of the hundreds of member groups and clusters that together make up the Laniakea supercluster, a structure 500 million light-years across that is already dissolving under the expansion of the universe. Laniakea itself is drifting toward the Great Attractor, which is drifting toward the Shapley supercluster concentration, all of it embedded in the cosmic web of filaments and voids that spans the full observable universe. Inside that same observable universe, Alcyoneus stretches its jets across 16 million light-years. IC 1101 extends its stellar halo across 6 million light-years of space and contains a mass 50 to 100 times greater than our galaxy's total. And somewhere in the direction of Hercules and Corona Borealis, a structure possibly 10 billion light-years across either challenges the laws of cosmology or represents a statistical feature that will dissolve under further scrutiny. The Milky Way, measured against all of this, is genuinely small. Not poetically small or philosophically small. Measurably, physically, quantifiably small. Its 100,000 light-year visible disk is a fraction of a percent of Alcyoneus's jet length. Its few hundred billion stars are 1/300th of the stellar count of IC 1101. Its position in Laniakea is peripheral. Its role in the cosmic web is that of an unremarkable node in an unremarkable filament in a supercluster that is one of thousands of such structures in the observable volume. And yet, the universe that produced IC 1101 and Alcyoneus and the cosmic web also produced this specific planet around this specific star, in this specific quiet corner of space. The atoms in your body were forged in stellar interiors that exploded billions of years ago, scattering heavy elements across the galaxy. Those elements eventually gathering into a solar system, a planet, an atmosphere, and eventually something capable of asking the question of how large the universe actually is. The scale is real. The smallness of our position is real. And so is the fact that we are the part of the universe that turned around and measured itself. Every number in this journey, every light year and solar mass and billion-year timescale was worked out by human beings using instruments they built, mathematics they developed, and ideas they refined through generations of collective effort. The universe did not hand us this picture. We assembled it, piece by piece, from faint signals crossing billions of light years of space to reach our telescopes. That is, by any honest measure, the most remarkable fact in the entire story. The largest galaxy we have ever found is 16 million light years across, ancient beyond intuition, and utterly indifferent to our existence. We found it anyway.